So yesterday we went through a overview of what the cosmic web is and what its properties are and what we observe in terms of its galaxy population, gas content, and even its dark matter content and its structural properties. So one of the justifications for studying it, I said, is because it informs us about the first stages of the formation of structure in the universe. And today I will be specifically talking about this very aspect. How does structure in the universe form? And in particular, the question, why does this lead to the formation of this intricate web-like structure in which you have filaments, cluster nodes, walls, voids, and etc. By now we have gained quite a lot of insight into the various underlying mechanisms in this, although the one overall mechanism is it's basically gravity. So what I will be talking about today is various aspects that contribute to understanding the specific properties of this cosmic web. That's a lot of material. It's more material than I can cover in 1.5 hours. So I will take a choice out of this, although in the slides you will find information on all of these aspects. I will start with a basic overview of what the mechanism of gravitational instability is about. That's where does structure in the universe come from? Where I assume, or where we are forced to assume, I should say, that most of the matter in the universe is indeed this dark matter, because if we assume that gravity is doing all this work, then the dynamical timescales involved force us to take the amount of mass implied by dark matter, even though, as we heard in the past 2 hours, we have no way of seeing the constituents of this dark matter. There are cosmologically overriding reasons to assume that this is the medium in which structure is forming. Now, when we look at the cosmic web, we see not only the formation of structure, but of course the structure assumes some structural properties. We saw the dominance of the filaments and the walls. So we have to ask ourselves, where then do these filaments and where do these walls come from? What is underlying the fact that they emerge in this structure formation? And we will see again, it's an intrinsic property of gravity, of gravitational instability. Yet, that still doesn't explain why these filaments and walls are woven together in this sort of network. Right? Why do the clusters connect up with filaments and filaments connected to walls and etc.? What's the mechanism that actually makes the connectivity of all these components? And we will see that understanding gravity in terms of tidal gravitational fields, the tidal gravitational fields induced by the inhomogeneous mass distribution, provides a main part of our understanding. So we will also talk about that. Then we set a step aside, because up till that point I have been talking about the anisotropic patterns that are forming, or the voids that are forming in this mechanism. But yesterday I also mentioned that one aspect is the multi-scale nature of the matter distribution. And that, of course, comes forward from the hierarchical way of building up structure in the universe. So that's an intrinsic part of this story, and we have to bring this in if we want to understand where we are now today. So once we have that, then we will actually go into something very specific, a mathematical formalism that combines geometry and some mathematics leading to what is known as the Adhesion Formalism, which is actually a beautiful way of describing the hierarchical formation of this web-like structure. Something that I've been working on the last year with Job Veldbrugge, a former student of mine, is related to this, and that is what I mentioned yesterday already. That is, if we want to understand structure really in all its depth, structure formation, it's no good to only look at space. We actually need to look into phase space. To come back to Guido's talk, in the back of our mind there's always the Boltzmann equation, isn't it? And that's what it is about. It's phase space, right? So we will see that actually by going to look into phase space, we encounter incredibly beautiful knowledge of where structure is emerging from. If I don't have time to cover this, I will actually skip probably the adhesion formalism and go to phase space, just because it's the most recent developments. Now, something that I've been working on for all my professional career, starting as an undergrad student, is the formation of voids, which in itself is a very interesting story, but I think that actually time will not give me enough space to cover this. The information is over there. Voids are in themselves very simple objects, but they have a very complex evolution. So that by itself is an interesting story, but as I said, it's very likely that we won't be able to cover that. So this is sort of the outline of understanding the formation, evolution, and dynamics of the cosmic web, and what we will be talking about. So first stage is the basic idea behind the formation of structure in the universe. We all know that structure in the universe was hardly present 380,000 years after the Big Bang at the epoch of recombination, when the cosmic microwave background, satellites and experiments looked out in the sky. The one outstanding observation is how incredibly isotropic and by implication homogeneous our universe is, to incredible precision. And it's in fact actually one of the pillars behind our understanding of the universe. The cosmological principle tells us that the universe should be extremely isotropic. And indeed, the overriding argument, the dominant argument here, is the cosmic microwave background. The cosmic microwave background, of course, also informs us, reflects the structure in the universe at that epoch. The temperature fluctuations on the sky are a direct reflection, one-on-one, with the density perturbations and the pressure perturbations when we talk about sub-horizon scales. So here you see a very nice depiction of the cosmic microwave background fluctuations on the sky, the sky turned inside out onto a ball, and this is a W map, observations of the cosmic microwave background, and what you see is the fluctuations in the temperature. Now the temperature is 2.725 degrees Kelvin, and that remains the case up to a precision of a millikelvin. And then we notice that we are moving with respect to the universe in one direction with 627 kilometers per second, leading to a dipole pattern for which you can correct, subtract that, and then you have to descend down to a level of no more than 10 to the minus 5 degrees Kelvin before you start to see variations. Imagine that you want to measure a variation of 100,000th of a degree Kelvin here in a room or wherever. You would never manage this precision. But now we know that the universe does have this, and of course it's incredible technological feat that they managed to map these small perturbations on the sky. And what you see is a very spotty face. Very spotty face of what we now know is Gaussian perturbations of a range of scales with a spectrum that we sort of expect emerging from the primordial universe. And this in itself is a direct reflection of the kind of structure that we saw in the primordial universe. In other words, there was nothing. It's incredibly uniform. When you would compare this to Earth, go out in the ISS and you looked at planet Earth and you wonder what's the profile of planet Earth. You would say it's globe, right? But you know that there are mountains, but you know, even when you know about the mountains, overall it looks very uniform and very smooth. How large do you think the mountains would be on Earth if it were comparable to the structure of the universe 380,000 years after the Big Bang? It will be around 60.4 meters. Now, my country, the Netherlands, is not known for its majestic mountains. We actually have one mountain, although don't laugh. The mountain is 120 meters high. And I know you call it a hill, but we call it a mountain. It's Peter's Mountain. And, you know, so if you look out at this landscape of the primordial universe, you should think about the Netherlands. That would be sort of representative for the cosmic microwave background. Something like the Himalaya or the Dolomites in Italy or the Pyrenees in Spain. Out of the question. They rise up at the level of this dipole, but not of these perturbations, right? So out of this almost smooth primordial universe must have arisen structure. So how did this come about? So in the end, it's all gravity, though even though the fluctuations themselves were incredibly small, they do represent small perturbations in density and therefore also small perturbations in gravity, right? So if you would zoom in on such a region in the primordial universe, you would see a very small landscape with some mountains and some valleys. And even though the valleys and the mountains are only in the order of 10 to the minus 5, of course what happens is that they induce slightly more of a gravitational pull towards the overdense regions and slightly less of a pull out of these valleys. So what happens is that these things, due to their perturbations with respect to the uniform density at that primordial time, that induces a slight inhomogeneous gravitational field, which you can just write down like this. So this is the gravitational field with respect to the overall gravitational field of the universe itself that is accompanying the expansion of the universe. There's a slight perturbation on top of it. It's extremely small in the beginning because this term is only 10 to the minus 5, right? So this is the overall density of the universe. And as you see here, well, it's a sort of Newtonian approximation. This is the 1 over r squared Newtonian force. On small scales, sub-horizon, sub-Hubble scales, you're sort of allowed to do this to some approximation. The idea is that these small perturbations are leading to a perturbation in the gravitational field. So you would think, well, then these perturbations in gravity are so small, I don't think they will manage to build up the majestic things that we see out in the sky. Not the galaxies or superclusters even, or the cosmic web. That, of course, all depends on this factor. because this is the normalizing factor of the overall density of the universe. That's where the dark matter story comes in. Normal amount of matter, our baryonic matter, indeed would not be able to produce, on the basis of this, in 30.8 billion years, the structures that we see. We do need more, and dark matter provides this, as I will soon show. So when you see this, then of course what happens, and zoom in, you see what happens. Matter starts to move because of the inhomogeneous gravitational field. When you feel a slight pull in this direction, you move into that direction. There's a migration flow. But as a result of that, you actually create larger amplitudes of the inhomogeneities. So the next step, the gravitational force inhomogeneity is larger and the pull becomes more. And goes on, and goes on, and goes on. That's an instability. So it's exactly that reinforcing instability that in the end may lead to structure that we see over here. And notice, by the way, this is a complete cartoon, but notice that the process is not isotropic. It is anisotropic. I will get to that in a moment. Now, of course, this is only true for very vast, large distances and radii, because on smaller scales, when pressure is having an effect, and pressure is having an effect in the pre-recombination universe overall, when radiation provides the pressure, but later on, when you look, for example, on galactic scales and even cluster scales, gas over there does provide actually a stabilizing force by pressure, by creating pressure that tries to push away, right? So you actually, when you look at it, there are two forces. There's the gravitational force, and there is, on small scales, a pressure force that tries to push it away. Actually, you need a certain amount of mass to overcome the pressure and let the thing basically contract and collapse. We call that Jeans instability. Okay, so this is the story. You have primordial density fluctuations. So here's a contour map with overdense regions in solid lines, dashed lines to be are underdense, and that causes an inhomogeneous gravitational field with respect to the overall gravitational field. As a result, you see the underdense regions effectively pushing things away. Of course, they do attract, but they do attract less than the average. The overdense ones attract more than the average. Because of that, you get a displacement of mass. Because of the displacement of mass, you build up mountains in regions where the density originally was higher. They start to grow. Therefore, again, the gravitational force becomes stronger, and you get a feedback loop like this, and that's the formation of structure in the universe, given you have enough material to build this up. So when you look at real large simulations, not the cartoon one like I saw over here, so here you see a zoom in on the Millennium simulation, the one from the Virgo consortium and Volker Springel, you see that this sort of would be the primordial conditions, where you see slight fluctuations. With dark, it's slightly less dense. Where it's light, it's slightly more dense. And then when you turn on the supercomputer that is following the gravitational force for 13.8 billion years, what you get is this. A beautiful network with a cluster in the center where the large overdensity was here, right? That collapsed completely into a clump like here, and that would be, when you would look at into the in the galaxy distribution, in the end would be a cluster of galaxies. And what you see is that around it, this large clump is surrounded by a lot of structure around it. And if you look well, you see that that structure is not homogeneous, it's not isotropic, it's filaments and it's walls. And in the filaments and walls, you recognize little clumps. Some of these clumps have a mass of around 10 to the 13th solar mass and would be recognized as groups of galaxies, but the very smallest ones would be the halos of galaxies. So what in the end you would see is a cluster of galaxies connected to filaments that are basically providing the bridges to the other galaxies. And when we look at the velocity field, of course, we saw that everything in the universe is moving, including ourselves, and they're moving along these filaments. Most of the stuff is actually transporting the material towards this clump, this cluster clump. So nothing as illustrative as a movie, and as I heard several remarks already by other speakers on the movies, let's show one here. Because here you see basically a box, a computational box, that's the redshift, and you see that there was a homogeneous distribution in the beginning, and due to the force of gravity, you gradually see the buildup of structure. You see the contraction of material towards these high density regions. You see the evacuation of the underdense regions, they're the voids. And look at the way the structure is forming. You see here a large void, but in the large void you see smaller and smaller voids. Actually, these smaller voids were the first ones to emerge. When you look at the filaments, you see here large filaments, but if we go back again and have another look, have a look and try to see, you see it here better on the screen than you see it over there, but the first things that you see emerging is these small little tendrils. And then you see here you see these small tendrils, they start to merge together. You see that? They move together in building up larger. Here you clearly see one. You see the filaments moving towards each other, and now it's a much larger filament. So here you see clearly what I told you already, this hierarchical buildup of structures, starting with small structures, building up larger and larger structures. Not only clumps, but also filaments. And you also saw the small voids that in the young universe were there, and gradually they merged together into much larger underdense regions. And gravity is the only force at work over here. So the only condition is gravity and, in this case, the right condition, the right description for the amplitudes of these fluctuations in the primordial universe. And everything here, what is usually shown, is predicated on this cold dark matter assumption. And the cold dark matter assumption over here is not so much the particle as well as the implication of the particle on the amplitude of these fluctuations, which follows exactly from what you do if you follow the evolution of phase space with the Boltzmann equation. Then what comes out is the amplitude at each of the different scales. And the fluctuations that you see is basically the sum of all these different fluctuations. That goes into the box together with the total amount of mass and gravity. That's all of the ingredients. And you see you are getting pretty much the web-like structure that we saw in the galaxy distribution, at least qualitatively, right? So, what we see here from this movie is three very important aspects. First of all, I noticed that you could see the small structures merging into larger structures, so that's the hierarchical structure formation. Then, clearly, the contraction and the collapse of matter fluctuations is not proceeding uniformly in each direction. There are preferred directions, and you end up with structures like filaments that are elongated or walls that are flattened. So we have to get back to that. The other thing that we clearly saw is that although those primordial fluctuations that you saw in the microwave background are totally symmetric between underdense and overdense, the final resulting mass distribution is far away from that. It is totally asymmetric, and that means that the overdense regions occupy far less space than the underdense regions. And that must also be a result of the gravitational force. Actually, what we see is that the underdense regions, because they were underdense, represent regions of less gravitational attraction. As a result, mass that originally was within these voids starts to move out of these voids towards the high density regions. That's why they're losing. But not only that, because of that, the void effectively is pushing away its boundaries, and it's expanding with respect to the overall universe and occupying more and more of space. The overdense regions, though, contract more and more matter, but also start, because of the gravitational force, to collapse to themselves, and therefore become smaller than what they started with, right? So that explains sort of the dichotomy between voids and overdense regions. So let's get to the aspect of the anisotropic collapse. Why does this process of gravitational structure formation lead to the formation of walls and filaments? Why is this so characteristic for the first stages of structure formation? Well, it all comes down to another instability aspect of gravitational collapse. So the first one I already mentioned. You have an overdensity. The overdensity represents more gravitational attraction than an average. Therefore, more matter is moving in, it grows in density, and therefore you get this feedback loop that more and more gravity leads to more and more gravity, and in the end, it overcomes all bounds and it starts to collapse completely, even with respect to the expanding universe. Now, when you think about it, and you would take, for example, a ball of matter that is slightly overdense. Now, if it even has the slightest deviation from a pure sphere, an ideal sphere, then the following happens. Well, here it's already a little bit flattened, but imagine this would be almost spherical. When you look at the gravitational force inside such a structure, you would see that along the smallest axis, and even the smallest deviation from sphericity has the smallest axis, the force is slightly stronger than at the longest axis. You can see this very simply. Draw a sphere inside this ellipsoid, and you see the sphere is completely filled with the overdense material. So that's stronger. But if you would draw a sphere around the outer region, then it involves also some of the less dense stuff of the surroundings, and effectively that leads to a smaller force along the long axis, right? So if you see that there is more attraction along the small axis than along the large axis. That means that the collapse along the small axis goes faster. But that leads to a strengthening of the flattening, right? Because it starts to flatten a little bit more in this direction than that direction. And that again is a feedback loop. That makes that the gravitational force along that direction becomes even stronger and stronger. So the collapse will go first along the shortest axis before it goes along the second axis. And if you're lucky, that is, if the thing is completely gravitationally bound, it will also collapse along the third axis. Not always necessary. It could be that it remains along the long axis like this. So what's the resulting structure? When you get a collapse along the short axis only, you get a flattened disk, a membrane, right? And when it goes on along the second axis, then you get an elongated pipe, a filament. So you see that when you think about this anisotropic structure is a natural outcome of the same gravitational instability thing. Now, of course, this is a little bit simplistic because this isolated object never is there. Now, on the other hand, the primordial Gaussian field certainly never has spherical objects. You can do mathematically the statistics of a Gaussian field, and you will see that the probability to get a spherical object is 0. They don't exist. So there is always flattened objects. But, of course, the evolution of this stuff here is not only that of an isolated object. There is an extra force on top of the gravitational self-gravity of this object, and this is the self-gravity term, this is the acceleration term, this is just the mass in the surroundings, and these are the force terms that are adding to such an object. This is just an ellipsoidal object, which is really simplistic. But what it very nicely shows you is 3 aspects. This is the self-gravity. That would also be there if the thing were purely spherical. This thing describes in each of the directions, m is 1, 2, and 3, x, y, and z. So it's the different directions, right? This differs for each direction and is strongest along the shortest direction. So you here have a force which is anisotropic. In one direction, the shortest, it's stronger than the longer axis. And then there's an extra term over here. Where does this come from? This comes from the overall density field. The overall density field in the universe is inhomogeneous, starting from the primordial universe. Now, when you do the gravitational, then look at the gravitational force that's acting on such an object. It's never homogeneous. The force here that it feels from the inhomogeneous mass distribution is completely different from the one there. There's a difference between gravitational force. That is, on that body, you have different forces at different ends. And we know that, of course, as tidal forces, right? That's what the moon is doing on Earth, and that's why we have the tides from. So that effect, anisotropic, because it's an anisotropic force field, adds to this anisotropy of the gravitational collapse. Here is a term that adds to this anisotropic force field. So when you look at any object in the universe and look at the gravitational force, it's always anisotropic as a result of its own flattening and as a result of the inhomogeneous distribution at all. That's interesting, because that couples its evolution along the various axes basically to the surroundings, and you can actually do the calculation for the various axes and see they will collapse at different times, and therefore you get objects of different forms and shapes. So how does this come about? Now here is a very keen following of the structure that results. So here is the cosmic, here is the basically the meta distribution, and in this meta distribution we followed the stuff that was elongated. That's the blue. And here is the stuff that was flattened. That's the walls. And now this is at a very early epoch, at an epoch of around a redshift of 9, that doesn't matter over here. And we follow its evolution in time. So what do we see? You see that actually the filaments are themselves moving and building up larger and larger filaments because of this anisotropic force field. And the same thing you see with the walls, and you see here a large void expanding, and you see here the large flattened objects that we see in the matter distribution. And this is basically the effect of the anisotropic force field. So you clearly see the walls and the filaments in the mass distribution. Some of them, the filaments, had the anisotropic force field that made it contract along two directions. The walls have been contracting along one direction, dependent on where they were exactly in the universe and where what the force field signature was at that point. Right? Now, if you want to see this in another way, you could, for example, imagine yourself sitting on a galaxy or a clump and look around you as the universe is evolving. And you look at the mass distribution, and here you see what happens. You see here a sky distribution of the mass around you, and you see it has quite some structure. Now, you would think that these are filaments, but that's not true. If you have a plane around you, and when you would be embedded in a plane, then you would see a circle on the sky, right? When you would be sitting in a filament, you would be seeing something there and there, so you would see two spots, right? So actually what you see here is a lot of small walls, and gradually, as time proceeds, you see that these walls start to merge, and here you only are left with two walls, and in the end these two walls merge into one large wall at the end. The build-up, the hierarchical build-up of the cosmic web. Filaments and walls. Here it is slightly less. Here you see ourselves sitting in the walls. That's a different spot in the universe. It's not a different cosmology, it's just a different location. Just happens to be one that originally was in a wall, but within the wall you see that mass starts to move to two clearly visible spots. And in the end, you see two spots into what originally was a disk-like distribution. So what happened is you were originally sitting in this membrane, this flattened structure, and in the membrane, the stuff was sort of contracting towards a filament, right? That was this story of first along the short axis and then along the second axis, producing a filament. So we do see these things. If you want to see how this works out in overall in terms of statistics, I showed you the movie and of the evolving filament population. Here you see plotted as a function of redshift the length of the filamentary network in the universe. And you see there was much more filament at high redshifts than as in the present day universe. Because what happened is that these filaments were basically moving together, forming more and more massive filaments, but that occupied less and less space, right? Originally, we started off with very small filaments, but as time proceeds, most of that stuff moved into larger and larger filaments, occupying less and less of space. The same with the walls. They're much less prominent now, in that sense, than they used to be, right? So here you see the evolution of the cosmic web. You could also ask yourself, how is this with the mass in these objects? Where does all the mass go? And where did it come from? So, for example, you could ask yourself, if at a redshift of 2, stuff is in a certain component, for example, in a filament, where does it end up at another redshift? So here you see redshift 0, redshift 2, and this is the stuff that originally started off in filaments, and you see that it moved out of the filaments. There is less stuff that originally at a redshift of 2 was at filaments. Nowadays it's far less. So where did it go? Well, simply look at the black line. It all moved into the clusters, right? this stuff in walls and voids, that's just sort of the fringes. The real important fact is that stuff is moving from the filaments into the nodes. But you can also ask yourself that of stuff that at a redshift of 2 was in walls. And you see there is less of that material. If you take the stuff that at a redshift of 2 was in walls, nowadays only 40% of that stuff is still in the walls. Because most of it, look at the orange, went actually into the filaments. So you really see the process. They went into the walls, and in the walls they were moving towards the filaments, right? And you can see the same from the voids. I told you that the voids are emptying. So you see that only 50% of the stuff that originally at a redshift of 2 was in voids is nowadays still in voids, because most of it moved either into the walls or into the filaments, right? You can also reverse the question and ask yourself, where did the stuff that nowadays is in the nodes, where did it come from? And you will see that most of the stuff actually comes from the filaments. And you can ask yourself the same question with respect to the filaments, and most of the stuff came from the walls. So you can actually follow the mass that is moving in this network, right? So let me skip this one. So how then does this all connect up into a network? Well, in the end, everything goes back to this thing. I told you this anisotropic collapse went along with an anisotropic force field, and this anisotropic force field is a tidal force field. Now, I could write down the gravitational acceleration, and as well I can write down the differential of the gravitational acceleration, that's the tidal field. And the tidal field is, well, this is a formula that if you study electromagnetism, you must know this thing too from Jackson. You clearly see this thing, right? And this is actually the mass distribution. That's the inhomogeneous mass distribution. So you could ask yourself, what does this imply for the force field, right? So you could ask yourself a question. How do I produce a filament? It's clear that to produce a filament, you must make things collapse along 2 directions, and not the third one. I can do that because it is the anisotropic force field. It basically means that if you look at the forces working on an object, that you should make it collapse along that direction and stretch along that direction. You can try to actually predict what happens. Because here you see the force field that you want to have. What is the average mass distribution that is evoking this? What would be a typical configuration in the mass distribution that evoke such a gravitational field? And actually there is a technique related to path integrals from high energy physics, which allows you to do this, to calculate this. And it's called constrained fields. It was introduced by Ed Birchinger. And actually when you use this and translate this, you can actually investigate statistically what you expect. So if you have a filament forming field, what would be the typical configuration? I showed you yesterday already the answer. The answer is you get these filaments like here, and this is actually the force field, like I showed you. You move along 2 directions, and for some reason you always see 2 clumps, 2 clusters at some location around these filaments. Why would that be? Well, such a force field is actually what we call a quadripolar field. So here you see what happens. So this is actually the game. This is the sort of the main thing. When you would look at the primordial configuration that would lead to a filament like this in the present-day universe, then actually the prediction is, and this is the location where the filament is that on average around that location you always have two mountains in the primordial field. Why? Well, when on average you have two mountains here, you produce a quadripolar force field here. These mountains will themselves collapse into clusters, and what you typically get is that the configuration of a filament is nearly always embedded into two mountains on either side, which actually these two clusters took care of actually producing the filament in between. So you can almost test, for example, computer simulations, but even the galaxy distribution, and ask yourself, if I trace a filament, can I recognize the clusters that are on either side, which were basically the agents to form this stuff? This means that the remark that I made about the connectivity of the cosmic web is actually embedded in the question of the dynamical origin of the cosmic web. It is no coincidence that we see always the clumps and filaments emanating from the clumps, because the filaments were induced by these clumps. And it's almost like the universe has been weaving a tapestry with nodes at some points, and in between the nodes, the threads, right? The threads are, the filaments are never randomly there. They're always there in between those clumps. And people have been looking into that in simulations, and indeed, you, for example, here, you see sort of the magnitude of the tidal force field, and you always see that even in the tidal force field, in the present-day distribution, you recognize these filaments, and very nicely, you see the spots, the highlights, that are basically responsible for the filaments in between. Right? So this is how the cosmic web has been built up. And this was actually the origin of the word cosmic web, because this idea was first pointed out by Dick Bond and Lev Kaufman and Dmitry Pogosyan in 1996. And they introduced the word cosmic web. From Sergei Shandarin, I heard that they got that from his daughter, who was married to Lev Kaufman. So that's a quite likely explanation that that's the origin of the word cosmic web, right? So it seems to be a family issue that has not yet been resolved, who is responsible, but it is something like that. So what they showed is that actually, when you lay down, for example, here at these black spots, the most massive clusters, you could actually calculate the tidal force field due to these clusters, and then calculate what would be the mass distribution that's coming out of this. So when you only have 5, you don't see that much of the emerging network. This is the original distribution, this would be the evolved distribution. But when you do 10, you start to see a sort of web-like structure. And when you have 20, you clearly see a network. So the idea was you really put down your clusters and then you have your filaments, right? So that's the idea of the cosmic web. Okay. This brings me back in time in terms of theory. Because, in a sense, a lot of this dynamics is going back earlier in time to 1970, when no one less than the great Soviet physicist Zeldovich came up with a very, very simple theory with tremendous insight, turned out later on. Here is Zeldovich, who in 2014 we organized a conference in honor of his 100th year since he was born. And so he's a very famous person. He even had 3 Soviet distinctions, hero of the Soviet Union. I can explain you where they came from, but they were not given for the Zeldovich Formalism, for which I'm giving you an explanation further on in this talk. Regretfully, that was not deemed important enough for another 4th star, but I think they should have given that to him. So what he did is very simply, it's actually something that comes from hydrodynamics. And here I'm coming back actually, I will coming back to this very often. So what you see here is actually looking at the mass distribution in a slightly different way. Up till now, I looked at it in the Eulerian way. I was looking at the distribution of mass as a function of position. But Zeldovich said, no, why don't we look at it in a Lagrangian way? So we are going to look at it mass element by mass element. And a mass element originally has a position q. And then, because of the gravitational forces of the inhomogeneous mass distribution, it's moving in time towards an Eulerian position, x, as a function of time. And he showed that in a very simple linear Lagrangian perturbation theory, very simple linear, first order, you could actually split off the displacement, because this is the displacement, right? This is the original position, and the mass element moves from its original position through the universe to a place q. And the question is, what is the displacement s as a function of t? And he showed to first approximation, displacement can actually be splitted in a temporal term, and in a term that only depends on the initial field, on the initial inhomogeneous gravity field. The time term actually turned out to be a universal term. It's the same for all the mass elements. It's the growth term of structure, the linear growth term. And it makes things extremely simple, because what it says is basically position plus some time term plus something that looks like a velocity. Right? So things move from its original position in a ballistic motion simply by original velocity times some time term. That's all. And the only thing that's left is that you can actually have to determine this time term. And what he showed, and that's where the crux of the Zeldovich approximation is coming from, that it simply is the gradient of a potential field. It's the velocity potential, not the gravitational potential, but in the linear approximation, that velocity potential is directly proportional to the gravitational potential. So it becomes incredibly simple. You take your initial mass distribution, your W map or your Planck map, you calculate the gravitational force field, solving the Poisson equation, in the initial position, then you take the gradient, that's all that you need to know, and for the rest it's just boom, moving the particles around. Now, he wrote this down in his 1970 paper, but at the time computers were not really showing what was going on, although they could imagine it. But showing it is something else. I will show here a small simulation in a box with a lot of particles that were inconceivable at the time, and just follow the formation of structure in time. What do you see? Out of the initial force field comes directly the anisotropic web-like structure that we discussed now before. He predicted it. It was there because in the original force field there was this inhomogeneity that actually corresponded to an anisotropic structure, of the force field and therefore of the velocity field that was directly tied to that. You just move the particles ballistically, and what you see emerging is the beautiful cosmic web. Bang! And you can see it in incredible detail. Now, of course, it goes wrong at a certain point, because here they're moving through each other. That's simply because there is no gravity stopping it. It's just the first order term. It doesn't have the higher order terms, because, of course, when mass is meeting each other, then that initial gravitational force is no longer good enough. There is some other terms coming in. That's not what it does. But the overall picture, the overall morphology, even quantitatively, was ingrained in there. Actually, it turned out that it was better than what originally had been conceived. It turns out that the mass distribution that you get from the Zeldovich approximation is almost perfect up to the moment that a stream of mass here is finally meeting a counter stream. Because then they go through each other, and you actually then see that something bad happens. Up to that moment, you can always say, at a certain location x, where the mass element that has arrived at that moment t came from originally. But not anymore when something came from the other side too, because then you have two streams. So actually, in that case, you should, at one location, sort of be able to distinguish between the two streams. You already feel the concept of phase space coming up here, right? So that's when the Zeldovich approximation starts to break down. But at hindsight, once we had large computer simulations, people started to realize that that whole approximation, so simple, was far better than had been originally thought it was. So it's actually a superb tool and still provides us with a lot of insight, and in particular a lot of insight why the density distribution is anisotropic. So, what is this thing of the Zeldovich approximation? In a sense, it is a mapping. It is a mapping that we also know in other fields. It is a mapping from an original position to a final position. I don't know whether you ever, for example, in the summer, have been in a harbor with a port with yachts, and you see the waves in the water, and you see the reflection of the sunlight reflected on the ships. And then you see a beautiful pattern of caustics, very much reminiscent to what you see over here, right? What you see here is a glass plate. You can do the same thing, a glass plate with an uneven surface. Therefore, the breaking, the refraction on the glass plate is inhomogeneous, and light gets distributed inhomogeneously, totally like the Zeldovich approximation. It's the same mathematical mapping. And that goes pretty far, actually. So, when you look actually what this is, and that's where we gradually get towards the concept of phase space, of course what's tied in with this is the displacement of mass. And here you see the velocity vectors in this little square, right? So notice that I'm talking both about the mass elements, the density, as well as the accompanying velocity field, right? So that's what the Zeldovich approximation is doing. Now, one more thing that the Zeldovich approximation does, and what you immediately can infer very simply from the accompanying Jacobian, you could actually from this thing immediately infer what would be the resulting density of mass that originally was at a position q, and then finally at the time t. When you do actually that calculation, you find this answer, and the answer is very insightful. This is the uniform density, but you see that underneath the line there are three components. 1 minus d times lambda 1 times 1 minus d lambda 2, 1 minus d lambda 3. The lambda 1, lambda 2, lambda 3 are actually the eigenvalues of this deformation tensor. That is the different, if you take a mass element, so you get displacement of mass, and in this direction it goes different from that direction, so a mass element starts to deform. It's all hydrodynamics in a sense. This is the deformation. And what you see, if you take the eigenvalues of this thing, that basically tells you in which directions a mass element gets stretched and in which directions it gets compressed. And you see that what comes out is three terms based on the eigenvalues. Now, what you see here, if you take the largest eigenvalue, let's say lambda 1, then the first term where d times lambda 1 becomes 1 is in that direction 1. What does it mean? Well, if this becomes 1, this becomes 0, that becomes infinite. That's collapse. But it's collapse along that one direction and not the other directions. So the Zeldovich approximation immediately showed directly that collapse will actually proceed in three stages. First collapse along the largest direction, largest in deformation value, then lambda 2, and if lambda 3 is larger than 0, if it's smaller than 0 it doesn't do anything, then it might collapse in the third direction too. Same for lambda 2, by the way. Right? So the whole picture of collapse towards walls and then potentially collapse towards filaments and then collapse towards clumps is in the Zeldovich picture. So this is what you see. So what you see is that actually mass that originally was evenly distributed actually gets gradually transported towards an overdensity. And you see that at the overdensity, stuff starts to build up a huge density excess. And only once it passes through this barrier of 2 lambda 1 is 1, then this thing becomes infinite. Actually, when you look at the accompanying velocity, you get something very interesting. This is what the Zeldovich formalism predicts. You actually get a stream of mass in this direction, right? But there is also a stream of mass coming from this direction, right? They're both moving towards the overdensity. So you see that when you look at the velocity around such a peak, you have stuff moving here and you have stuff moving there, and then it passes something like there. And then at a certain moment, catastrophe happens, literally, mathematically speaking. At a certain moment, when this thing becomes infinite, what you get is that each of these mass elements went up here, and then you get a vertical line connecting up to here. So you get the two streams coming from both directions with a lot of mass elements all having arrived at the peak in the density field. Literally a catastrophe, because a lot of the mass elements that originally were at different positions all are at the same position. That's where the infinite thing starts to happen. Then what happens next is that actually these mass streams move through each other, and you saw that in the movie. So suddenly, at one location X, you don't have one stream, like originally you had one there, you have three. You have one moving in this direction, you have one moving in that direction, and one in between. You couldn't tell anymore where a certain velocity belongs. At any one place, there is stuff moving this direction, there's stuff moving that direction and that direction. Right? That's what we call multi-streaming, and that's where, over the past 6, 7 years, a lot of theoretical work has been going into in the realization that the buildup of this structure is going along with multi-stream currents in the universe. Right? So this is coming back to Zeldovich, so this is the original field, and this would be sort of the final structure. I'm coming back to the phase space evolution. I will be concluding with that after going into the hierarchical evolution and the adhesion. Because up till now, in the Zeldovich formalism, we haven't said anything yet about how large the structures are. And while we saw in the embodied simulations that we had structures on small scales and large scales. So how is that working together? Well, Zeldovich has a little bit of a problem there, and you can already understand it because you didn't ask and I didn't tell. But when I was describing this force field or this density field, I didn't specify on what scale. But density is, in a sense, almost a non-existing physical quantity. When you say the density here is such and such, that's never complete information, because you have to ask on what scale. You have to average an amount of mass over a certain scale, and that needs to go into it. And that's not yet in the Zeldovich formalism. So I already told you yesterday what the result is. You get this multi-scale structure in the universe with large filaments, but also these small filaments. And they do not come from the same scales, right? The large ones came from the largest fluctuations and ate up a lot of the smaller ones, but a lot of the smaller ones have survived. And each scale you have to basically look independently. So when you would look, for example, at a mass distribution like this, and here you see basically what happens with a couple of filaments that are lining up together. You see that they merge into one large filament, and in the filament you have a lot of clumps. So you have clumps on a small scale, filaments on a larger scale. Originally you started off with smaller filaments, right? Like this. So the idea is that actually what happened in the universe is that this evolved hierarchically. What that meant is that when in the original box you have some small clumps, these small clumps were emerging from small fluctuations, small in terms of size, but given the spectrum implied by the cold dark matter, the fluctuations on these small scales had the highest amplitude, and therefore they were the first ones to collapse. Then these actually merged together into larger clumps. What actually happens is that the fluctuations on a larger scale collapse. So the merging of the small scale clumps is the collapse of the larger clumps. And you can follow this whole thing through up till the present day. Well, this is very characteristically for clumps that build up from smaller and smaller clumps that merge, and then you get merge and you get a complete merging tree of structures. But you can do the same for filaments, as I showed you, right? So here you have initial mass distribution, and what you see is small tendrils. The small tendrils start to move towards the principal direction, and gradually they merge into a larger filament. And voids. So here you have a rendering of what happened to the void distribution, starting with the void distribution at a redshift of 2, identifying them in a particular way, and then you follow what happens with the mass distribution. You see these small voids merge into larger and larger voids, into an ever-continuing story, hierarchical buildup of structure, right? So the hierarchy is a clear aspect of the buildup of the cosmic web. Problem: How do we tell, for example, a simple picture like Zeldovich? How to do this? Well, you could start filtering and smoothing on a certain scale, but it's not very systematic, is it? It's not natural. And actually, I have to disappoint you, Zeldovich fails here. So the overall picture on a certain scale is described up till the moment that streams on those scales start to meet up, and then up to that point it's a decent approximation. Nonetheless, one of the most interesting and arguably the last major contribution by the Soviet Union to cosmology was made in 1989 and was called Adhesion, and was an extension of the Zeldovich picture. And actually it turns out that by doing so, they did provide a really deep understanding of the hierarchical buildup of the cosmic web. So let me pause a little bit to this aspect. Coming back to Zeldovich, you get the following. So this is again the Zeldovich picture, this is the accompanying velocity field. When you actually would look at the Euler equation, the force equation that accompanies this, written in this particular form of velocity, you would see that it looks like this. So for those of you who recognize it, this is the time term, this is the coupled velocity term, and remember from the Euler equation that you actually should have a force term on this side. So actually the Zeldovich equation corresponds intrinsically to an absence of a force term. That's why things move along uninterrupted in a ballistic motion. There's no source term, right? So that's what's wrong with the Zeldovich equation. So the way to repair this is to put in the gravitational term. The problem is then you have to solve every time for the gravitational term. That involves the Poisson equation, and actually what you're doing then is what people try to do with n-body simulations for little discrete particles. Well, shall we go then to the n-body simulations? Well, that needs huge computer resources, and in the 1980s in the West they did have these computer resources. They already had FAX, what was it, FAX 380 or something like that, in which they run these massive simulations of 32 cube particles, for which the Gruber Prize was awarded actually. But nowadays it's of course no alternative. Also at the time, for the Soviet scientists, it was not a very good alternative. So they actually came up with a much nicer idea, an analytical idea, which actually in the end provides much more insight. There was actually, what I understood from Sergei Shandarin, at some moment, some plasma physicist, I forgot from which Russian university, was attending a talk of the group of Zeldovich and saw this and noticed, but you know, we are doing something similar, but we actually put in another term on the other side such that we can deal with it. We put in a term with a viscosity in there and a second order derivative of the velocity. I don't know whether you recognize it from, for example, hydrodynamics. You might think of the Navier-Stokes equation. Actually, this particular form has even a name, and it's called the Burgers equation, called after the Dutch hydrodynamicist Burgers. There's a large institute in the Netherlands for hydrodynamics in which they're calculating, you know, how our rivers and harbor and ports are dealing, etc. That's the Burgers Institute. So this guy was actually involved with this. So know what? This is one of the very few hydrodynamics equations that have a complete analytical solution. So that was great. They could do something with this. So they could solve this equation, which at hindsight is nothing more than an extension of the Zeldovich formalism by putting an artificial force term that simulates self-gravity, sticky, adhesion, right? So they did that, and what you actually get is a formalism that allows you to follow for any velocity potential in the initial universe, and this is basically the potential that is the input from the initial positions, a Gaussian landscape. Actually, the Burgers equation can be solved for this. You can actually find a solution between the original Lagrangian position and the final Eulerian position and find the solution, but the solution is ugly. The solution is here. This is the gravitational potential at a position nowadays, at the position x, and you here get a quadratic term, and this is the original Lagrangian position. This is the original position of a mass element m with the original potential, gravitational potential, plus a linear term over here. It looks ugly, but it's actually tractable. You can actually predict and do something with this analytically. You can actually look at the properties. Now, one thing that you see is a quadratic term here in the Eulerian coordinate and a quadratic term in the Lagrangian coordinate. So one thing you could do is say, okay, I'm concentrating on the initial gravitational potential, and I see that in time I'm going to add this quadratic term. It's like you put a thing on a parabola, right? So what happens now? I have to identify the positions x with a position q. That is, at every position nowadays, I'm going to look where are the mass elements that originally were at q that now ended up at me. That's easier said than done, but you can solve it from this equation analytically. The solution is not trivial. It was done by my PhD student Johan Hidding, who's a real genius in this thing. And he did something alternative to what originally was done in 1989. He actually translated this into geometry. So what he did is he said, okay, well, look here. This is this is 1D. This is the original potential, and you go from this one. Let me see, from this one to this one to this one, right? It gets more and more curved. Now, the important thing is when you look at this surface and zoom in, you see the following. If it's just convex, it's easy. Then you can see, okay, this x came from this q. So I can do that. So that's what this thing is. Also here, everything is still one-on-one, monostream regions. But in here is suddenly a shock. There is a region where you don't know where to go to anymore. All of these things you cannot map to their original position. They actually stuck to these positions. That's where these things are. These things, these white regions, are actually stuck in one position. And it's not one Q, it's a whole bunch of them. It's simply mass elements have meeting up at a certain position in space. Now what you see, as time proceeds, you actually see that these mass elements move into larger and larger chunks of mass, and at the moment you even see them merge. So this adhesion picture actually has the hierarchical evolution of mass, right? Here you see what happens. So here you see the peaks that correspond to these regions in Lagrangian space. They are actually in Eulerian space peaks because they collapsed. And then these small peaks merge into larger and larger peaks. And here you see the outcome. Okay, I guess that some of you are confused. This is indeed demanding maths, so nothing better than a movie. I won't explain about the geometry that Johan accomplished according to this. He actually solved this fully three-dimensional by not looking at the lines, but looking at the surfaces. And I will come back to that in a moment. So what does this yield you? This is the same thing. I hope you can see it. It's a bit, you should see it here. You should come here later. You actually see the same thing as for the Zeldovich original distribution. But then, as the mass elements are passing, they get stuck because of the self-gravity. And what you see here is actually the small, so I invite you afterwards to come here. You see the small mass elements actually, you can see here small filaments merging into filament. You see it here? You see the voids moving up here. It's this process of things moving up. And it's not clumps. You actually see the elements of the cosmic web merging into larger and larger structures, into a totally natural means. It's in the formalism. And you can do the statistics of, how much is in filaments, how much is in walls. Now, to give you a little bit of a clue of what he did, he actually looked at what is called the so-called Baloney Tessellations. This is things from geometry, defined by the peaks in the surfaces. And then he said all the stuff that is in between these peaks. Imagine a mountain landscape. So you have a mountain there, and you say, well, all the stuff that's in between gets caught into one structure. Of course, it depends on your valley, basically. So if you have a valley where the peaks are basically lined up along two walls, then you get a wall. If they are in 3 dimensions along 4 peaks, then you get actually a clump. And the filaments are actually the ones where you have a valley running in between 3 peaks. It's pure geometry. The whole calculation was done within a fraction of a minute on a laptop using a computational geometry algorithm. Nothing of n-body simulations. If you want to understand here the Eulerian evolution of the cosmic web, you see its hierarchical evolution. The red is the clumps, the blue is the filaments, and the white is the voids. Geometric evolution. So, let me, given the time, actually proceed immediately to phase space evolution, because I've been telling something about it and I'm very enthusiastic about this, immediately follows up on this. I've been now indicating to you phase space already several times. It's clear that normally for any physical system, Boltzmann equation, I'm thinking about it every day of my life, Q, the velocity and space x, 6 coordinates you need. Well, in the context of the Zeldovich approximation, you might say, well, Q actually corresponds to U, the velocity, so I may as well talk about Q, right? So I look at the original position and connect it with X, the Eulerian position. That's the full phase space evolution. Now, what I think one of the most insightful theoretical realizations of the past years was made by 3 groups. One was Mark Nyrink, the other Sergei Shandarin, and Tomei Bell and Oliver Hahn. They actually were thinking, you know, when you really think in terms of fluids, what these n-body simulations do is totally simplistic. Because what the n-body simulations do is the following. They take an initial mass distribution, they grid it, and each of the grid cells becomes a particle, everything in a dot. And then you let this particle move. But then, of course, you have a lot of open spaces where you don't say anything. But that's not the way physical systems evolve. Not at all. And may I have 5 more minutes, Chair? Okay, so I need it. So actually, what you really should do is take an initial tessellation of space, a tiling of space, and consider each element, each tile, as a mass element. And you follow that mass element in space, not only its displacement, but also its deformation. Right? So some of them get stretched, some of them get compressed. If you look well, you remember now the adhesion picture that I was showing you, right? That's where we are. And you see the cosmic web coming out. This is much more natural. This is what hydrodynamic equations tell you things are about. Again, let me show you the difference. This is a movie made by Johan, my PhD student, the particle distribution. So this is the convincing particle distributions, the n-body simulations that we're talking about, right? Well, you see it's going extremely well in the high density regions where the clumps are. But we start to have resolution problems even to follow the filaments, which are pretty high density. The walls we hardly can follow anymore. Let's do the same simulation in a different way. You follow the mass elements. And look at this. Isn't it beautiful? This is actually looking at the phase space structure and taking into account the way the mass elements deform and displace this. You can actually follow the whole cosmic web by carefully following it in this way. So several people noted this. Why is this so much more superb? Well, what you actually do is the following. This is what phase space is about, basically. So this would be your original distribution, and this would be the velocity, this would be the position. So what is gravitational collapse? Gravitational collapse is actually mass streams moving up towards each other, and then gradually in the high density regions, in phase space, it starts to curl around each other. So actually the distribution is not a peak in the density. You should see it like a sheet in a 6-dimensional space. And then you see, well, here it's a line, but in reality, it's a 3-dimensional sheet in a 6-dimensional space being wrapped by gravity. That's a much more natural way of explaining this. Why was that second movie so much better? Well, that second movie picked up that here, 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 and here, you get a catastrophe. That is, you're accumulating more initial mass elements in one position. So that's where you see structures. That's much better than averaging like the n-body simulation is doing, right? So what you actually see is you get structures like this, right? So the phase space structure is infinitely more rich and allows you to look at the different aspects and to put things together. So what you call density is nothing else than simply a projection, an integral, along the velocity distribution. But it's nothing more than that. That's what it should be. So how then should we imagine the cosmic web? Now I showed you this little curl. Now this is more realistic. So what you see here is what you see is this. This is basically the dark matter sheet. You should, of course, I can't depict 6 dimensions, so this is 3 dimensions. One direction is velocity, and velocity translated into Lagrangian coordinate. This is the Eulerian plane, 2 directions in the plane. That's what you are seeing. But what's really happening because of gravity is the folding of this sheet in phase space. So what gravity actually is doing is the following. And notice the deformation of the sheet, and in particular its projection, because the projection is what you observe. See, the sheet is deforming, it's different streams coming together, and what do you see in the projection? You see a nice cosmic web. With the filaments, the walls are basically corresponding to the regions where actually in the sheet you get 3 folds. You're basically folding it like this, and what you see is a sheet. When you see a filament, it's actually went from 2 sides, so you actually get 5 wraps. And you can actually go, like Sergei Shandarin has been showing in recent papers, you can go to 10,000 stream regions, which are actually in the nodes, in the halos of the distribution. So that's actually absolutely beautiful. Now, just to conclude very fast, because this is work that I'm working on now with Job, and Job is, in my view, brilliant in this thing. There was a famous Russian mathematician, Arnold, who actually was able to quantify the various wraps in this phase space wrap and identify them with structure. He actually worked together with Zeldovich and Shandarin. But they never managed to actually tie this into the structure that was forming. Job did. So what he did is the following. He looked at the deformation field, and when you look at the deformation field, you have to look not at the densities, but you have to look at the deformation tensors and the eigenvalues. So you have to look at the field of the eigenvalues. And as I told you, those regions that originally had d lambda 1 is 1 are the ones collapsing. That, for example, would be these things, and that would start along this line. When you would map this to a Eulerian space, it looks like this, and this is what Zeldovich called a pancake, with a little cusp here and a little cusp there, and the cusp is actually, when you look this phase space sheet, it's the fold, right? So you're wrapping this thing, and that's where the fold is. And you can actually mathematically predict where that fold is. That was written down in a small equation, and you can actually develop a sort of intuition. So this is the initial position, and here you see where basically the outline of the pancake is, and the A3 is actually where these cuspy things are. So what you see here is the blini, the pancake. That's where the walls are forming. Now, to do this in full 3D was never managed. Until Job basically managed, and now I basically go very fast, I excuse that I have to go. He managed to derive the equation for these lines and sheets on the basis of the initial deformation field, and to write down the conditions for forming these various structures. So it may be complex for you, but because we're now going fast, but it's basically the quantification of the folds in this sheet. And you get all kinds of forms, butterflies and what you have, butterflies, cusps, and all these kind of things. So here you see basically the field, the contours are basically the deformation values, and on there you can identify where the different structures are forming. And so Job basically derived the condition. And the condition turned out not only to depend on the eigenvalue, but also on the eigenvector. So then he derived, for given initial positions, the eigenvalues and the eigenvectors, and on the basis of that, he was able to show that, for example, here you see the underlying network, and you see that indeed you can follow these things with lines, and the little dots correspond to other kinds of faults. That's the butterfly faults. So nothing as good as a movie. So here you see what he did. You see here the sheets that are forming in this particle distribution. Now I leave it up to you to judge what is better rendering of the underlying structure. Here's the sheets, there's the particle distribution. Here you see the sheets, and on top of it you see the density field, and you see that he basically managed to identify the sheets. But the nicest one, I thought, were the filaments. Because he managed to go one step further and identify actually the filamentary caustics. They're called A4. And you can even go to the nodes, they are A5. And you can actually see how they are all connected into a network. This is his spaghetti. And so this is in one go. This is not even solving a geometric equation anymore. This is just solving on the basis of the initial density field. You calculate the deformation field. You subsequently calculate the eigenvalues, the eigenvectors. You solve for those caustic conditions. You find where the ones are the conditions for the so-called A5, and you immediately have the spine of the cosmic web. Now, I realize that this is going a bit fast for the latter part, and it's also only meant as an advertisement. This is something that is about to, the first paper was put on the AstroPH, but these simulations are coming out soon. It's a completely new way at looking at the connectivity of the cosmic web, but it turns out that analytics here are allowing us to do this. You don't necessarily need n-body simulations for doing those things. So I think I should leave it up to him. Thank you. So what this basically is based on is a simple lambda CDM initial density field with Gaussian initial conditions. So you simply generate them in the conventional way. And from that initial Gaussian field, you subsequently determine the deformation field, etc. You actually do it all in Fourier space, so it actually goes in one go. And that's how you get this. Yeah. It's
I'm asking this question pretty often on this conference. According to all this, considering all these anisotropic processes, can we talk about conservation laws because of anisotropy?
The usual conservation laws, the one of the conservation of mass, continuity equation, the Euler equation, conservation of momentum.
They're working, yeah, because I was asking because of the theorem about angular momentum conservation, the space should be isotropic, and in result we will achieve angular momentum conservation. That's why.
That's a tricky question. Yes, that's true as long as there is no multi-stream regions. Right? That's a fundamental theorem from hydrodynamics. Once you get multi-stream regions, you can actually start to induce vorticity. Right? Which is not there in the initial, if you look at the initial velocity field that we are dealing with, it's basically a scalar, based on a scalar potential. That's why you had the the velocity potential, and it only has a divergence term and a shear term, but no vorticity term. Because you can actually prove that if there were vorticity in the initial universe, given that it's homogeneous, it would die out very fast. So it's presumed that there was no vorticity. There's also no indication on the cosmic microwave background for anything that resembles vorticity. So you could ask yourself, at a certain moment, generate vorticity. And actually you can generate vorticity once you get multi-stream regions. Right? And that's where actually the filaments are the sites where apparently a lot of vorticity is induced. There's some very interesting papers by Christophe Pichon and his collaborators describing this. Okay?
Any other questions? I should go back to you.
Yeah, I have just two questions. First about Berger equation. They are number squared. It is gradient of divergent of velocity. Okay.
Yeah.
And nu there is viscosity.
It's a viscosity, and it's a total artificial viscosity. It's nothing to do with the real viscosity that we deal with in fluids. It's a modeling of gravity. It's a sort of poor man's job. But with the great advantage that you could analytically solve it. Actually, what you assume is that the viscosity term is there, but its limit goes to 0. Okay?
And another question is about slide before the slide name, not title, shaping Tratata.
At which
there was an integral with function, like bipolar field.
you mean the one of the tidal force field?
Yeah,
You mean this one?
yes, exactly. Well, I have a question why it so look like bipolar field.
It looks like a quadripolar field.
What?
Quadripolar.
Yes, exactly. Why it's so different.
Tidal force field is a quadripolar field.
Okay.
Comment. According to this, what I remember, there is in 2 papers, which were small booklets, written in Russian. Zeldovich mentioned Arnold caustics. This was, I don't know if these papers were also published in English, but probably not.
Well,
It will be probably the Institute of Equality Mathematics or things like this. The small booklets which outside is part
yeah,
was not appearing.
I know that.
You know this,
I know of them, and Job looked in particular very much into them. There is one paper that has been published in English. The other one was not published in English, but translated in English, and we had to ask Sergei to get a copy of that. So, but what he had not is this eigenvector aspect, and the eigenvector aspect is all important to be able to infer these, the filaments and the walls and all this kind of stuff.
Any other questions? Now all of you are fine? Seems so. Then let's thank the speaker again.
Thanks.